Yes, I would like to tell you about large-scale structure cosmology of artificial intelligence. So this is a topic I've been thinking about for some time, and exploring how machine learning and AI can help with constraining cosmology parameters from large-scale structure. And I was specifically thinking, is there something that AI can bring or machine learning can bring that we otherwise are not able to achieve? So some kind of advantage that otherwise would be impossible or very hard to get with conventional methods. And so in this talk, I would like to tell you what I found over the last couple of years and where I think the most beneficial applications of AI in cosmology will be in the next years, decades. So let's start with a little bit of a background. So sorry, I just need to move my window here. Yeah. So in large-scale structure cosmology, the background is we would like to understand cosmological parameters. We want to measure the values of parameters. We want to test the laws of gravity. We want to find out what dark energy models are agree with the data. And the source of information about these is the structure in the density field. Right? So what you see here, probably very familiar with, is a simulation of dark matter. And you can see that this is a late time snapshot. You can see that it contains a lot of complicated patterns. And what we commonly use in our analysis is the power spectrum of this type of patterns. But what you can see is that it it's very complicated. It's way more complicated than a Gaussian random field. And it has a lot of different elements like halos or filaments or networks. So it's a very rich data set. So this is the type of objects we want to study. And the properties of this object, the statistical properties, will give us information about the cosmological parameters that underlie this universe. So just to compare, if we have an n-body simulation, this is a thin shell on the sky, it can have all these patterns, and let's say it has some power spectrum, and if we render a Gaussian random field with the same power spectrum, it will look like this. So those two maps have the same power spectrum, and you can see how much more complicated these patterns are compared to the Gaussian random field. And critically, the standard methods that we use, two-point functions, correlation functions, they only probe this type of patterns. So if this was our universe, then two-point statistic would be sufficient, statistic for this type of data, would get all the information out. But the dark matter distribution is more complicated, and we can exploit that in our analysis and try to recover more information that goes beyond the 2-point to constrain the parameters better from the same data. Of course, we don't observe this type of data. This is a simulation. We don't observe it. We observe the dark matter distribution, a large-scale structure through a number of different probes. And this is just an illustration from the illustrious CNG simulation where we have dark matter. So this is some type of data I would maybe try to map using gravitational lensing. You can have also other properties one can map, galaxy clustering. And those are then projected typically for example, a photometric survey. It's also we projected against the kernel. So we are looking at the universe in very thick 2D slices. So to work with this complicated object, AI methods can be particularly well suited for that. So AI methods work on, especially the modern ones like deep learning, they work on the full image level, right? They can crunch through a lot of pixels. They can crunch through data volumes that have been not possible to use before, especially that now the graphics cards are becoming larger. We have more memory, we have larger computers, so we can really do an analysis on the pixel level, treating the simulation like an image and analyzing that directly instead of summarizing it first into 2-point functions or other summary statistics. So this way, if we do that and we are clever about it, and we have good AI algorithms that we can effectively train, we can try to reach the information floor of the data. This is a very ambitious goal, but analyzing the data on the pixel map level rather than on summary statistic level can bring us closer to that goal. Now, the other ways that we can include AI in our pipelines is through accelerating simulations. So again, here, AI understands images. It can also understand voxelized data. So we can employ some of these techniques to make simulations run faster, or we can paint the effects from one simulation to another. I will come back to more details about it later. And finally, the third idea about how we can exploit AI to get an advantage for cosmological analysis is to do a multi-probe AI analysis and try to break the degeneracies between cosmological parameters and systematics, specifically, for example, astrophysical models of, let's say, intrinsic galaxy alignments or galaxy biasing. So this is a potential avenue of benefit as well. So all of these are still early days in the field, and we've been mostly working in this part here. So using convolutional neural nets to analyze large-scale structure data, but also recently started looking into accelerating simulations and multi-probe analysis with the objective of breaking some degeneracies. So now let's start with this part. So generally speaking, as I said earlier, we have different cosmological models can give us different distributions of dark matter in a statistical sense, right? So this is just an example to illustrate it. We have some fiducial cosmology, which is, let's say, close to what observations are giving us now. And we can draw a simulation at different values of cosmological parameters. And if we move away from a different cosmology, the patterns will look different. You can even by eye see here the statistically very different, even beyond the just standard 2-point. We can probably even classify the cosmology by eye if we wanted to. Specifically, quite interesting is how one can see the difference in dark energy equation of state. So measured by this W parameter, if we make it dramatically different, we just, maybe it's not super clear from this picture, but you can, in the paper, there's the same plot. You can see that the voids are getting much deeper and more pronounced. So even just exploring this by eye is quite interesting. So yeah, so the idea here is that if we use this simulation directly as a theory prediction, we can employ AI algorithms to analyze this as maps. And I'll start with gravitational lensing as the topic I'm most familiar with, spend the most time working on. This is a gravitational lensing map without any noise, how it would look for different values of this cosmological parameters, sigma 8 and omega m. And just to note that the values of sigma 8 and omega m, or the combination of those called S8, is currently a very involved topic of investigation, because we see different values of S8 being measured from lensing surveys, from large-scale structure, as compared to what the cosmic microwave background is telling us that we should expect at the current time in cosmic history. So there's a tension between S8 measurements in CMB and from large-scale structure, and the source of this tension is not really understood very well yet. Yeah, so this is why I'm focusing on this. Also, lensing can measure these two parameters the best. So for now, let's stick to those. You can see a little moon to give you an idea about how big this patch on the sky would be. And yeah, you can see clearly by eye that those structures in these maps are different. So how do we connect a map like this to values of sigma 8 and omega m? In a conventional, so generally speaking, what we need to do, we have some observations. We assume some model with some parameters. We assume some priors on these parameters, and we compare it with observations, and we obtain some measurement. This is the dark energy survey year 3 result that I was also involved in creating. So the way to compare with observations is the key variable here. And typically what is done, and it's a very well tested and understood method, it's a classical method. We create, for example, 2-point functions, which is basically a power spectrum or a 2-point correlation of the map. The nice property of that is that if we have a 3-dimensional P of k, so a 3-dimensional power spectrum, we can predict our 2-dimensional projected map power spectrum. by quite straightforward analytical integration. And so, of course, this part, the nonlinear part of this three-dimensional power spectrum has to be calibrated on simulations, but this is a much more easier, straightforward exercise than just using simulations themselves. So there are various ways to do it through Halo model or others, or through emulators, but nevertheless, after having that, the rest is relatively analytical, straightforward. So we compare the power spectrum that we predict with the power spectrum that we measure, and we can, through a Bayesian measurement, get our constraints. So if we want to use the image level analysis, the map level analysis with machine learning, what we can do is to substitute the analytical theory prediction from the nice equation that we know and like by a lot of numerical simulations. So we start with a large set of n bodies, and as we said, seen in the previous picture, we can generate them on different values of cosmological parameters, right? So what we do, generate a big simulation grid, produce a lot of these maps. Now here, we need to make sure that they look like the data, so they have the same noise properties, they have the same masks, all sorts of systematics are well included in that. But when we have that, we can compare the maps that we get from observations, simulations, through a convolutional neural net. And in this scenario, the convolutional net will be trained on simulations. And after it's trained, we'll give it an observation that we have. And the net will give some output that we will later on interpret in a probabilistic way, in a very similar way, actually, that we interpret the output of power spectrum. And it will give us constraints. So, of course, these constraints are, this is just a cartoon, so these are not actually the one made by the neural net, but I think you get the picture here. So this is the idea. Any questions at this point? Okay. So some question? Yeah.
Yeah. When you're training the network, do you need the images of the simulations to have like similar conditions as the ones in the data? I mean, you're not directly comparing the simulation on the data. Right? You don't need the same, you know what I mean? You don't need to be comparing like peaks with peaks and things like that. You're just comparing the structure in there.
Yeah. So I think if I repeat the question, so the question was whether I need, when I'm comparing on the structure level, or do I need to compare on some features, right? Yeah. So exactly. So the idea here is that the neural net learns how to extract features, right? Automatically. We don't have to use our own intuition here. We do very often for different types of measurement, like peak counts or 3-point functions, anything that we can compute of the maps. We think, oh, it's a good idea to compute voids or Minkowski functionals or other things. Here the network learns to automatically extract features, and this is the a different way of looking at the problem, where we kind of give up on our intuition. Just tell the machine, hey, find me the most important features that will give us the most information, and we will use those, right? Indeed, using our own intuition is also very important, and there is a number of projects that I'm also involved with that use peak counts, for example. But yeah, in this framework, we want to relinquish that responsibility.
So the training would be a bunch of realizations for a given set of cosmological parameters, and you're in the training stage, you're telling it all the simulations are produced with this kind of parameters.
That's
you
right.
Do that for a bunch of cases.
Yes, that's right. Yeah, yeah. You give simulations that are labeled, so every simulation like that goes with a label. This comes from sigma 8 of 0.8, right? And then the network learns how to discriminate between those. Very good question. Thanks. Okay, so right. So this sounds potentially quite interesting, promising, maybe. We can really try to optimize our features to get the most information, but how much can we get, right? Is it worth to invest time and effort into simulations and training all these machine learning models? Especially for, let's say, for stage 3 or stage 4 surveys, what's the advantage of machine learning? Is it 10%, 20%, 40%, 100%? So with that question, we started to look at some time ago already into these different regimes of data. So we started with these two criteria. First is how well we can measure our gravitational lensing maps. So what's the quality of observations? So if they are more noisy, then of course the quality is worse. And what's the quality of simulations that we can make? So how big of a resolution can we trust our simulations? Let's say so if we smooth the simulations, smooth actually the images more, then we don't have to include small scale modeling very much. But if we keep the simulation at very high resolution, so we use a very small smoothing scale, then we include more information from high resolution features, which obviously would be more beneficial for the analysis. So in this regime, we explored different configurations. And for a feasibility study that was done with kids that was kids 450 in mind, we found out that for a fiducial configuration of like relatively moderate smoothing scales and kids level of noise, we find that CNNs can outperform the power spectra by around 30–40%, which is a really nice advantage. So there's not so much nonlinear information because we don't go to very small scales, but nevertheless, it's important enough that to give us a lot of advantage on these sigma 8 and omega m parameters. And 40%, what does it mean? If we wanted to improve our constraints by 40% without doing neural nets, just with power spectrum, we would have to take roughly 50%, 100% more data. So we have to observe for another couple of years to get to the same result, which is not straightforward. So this is the way to improve the information gain from the data I already have by basically doing a more complicated statistical analysis with simulations. Okay, so very promising. Another thing that we observed that if we have better quality of data, so we have more galaxies per square arc minute, so noise level is lower, we maintain the advantage. So the networks are not so sensitive to how much noise there is in terms of comparing to power spectra. On the other hand, if we increase the smoothing, so we remove small scale information, we get the advantage goes down. So we lose the advantage. That is what we expect in the end, because we know that if we smooth the data a lot, we are left with large scales, and large scales are quite well modeled by Gaussian random fields. So that's in fact this trend shows that there's just this advantage here of the neural net. So higher is better. If we smooth the data a lot, then we lose the advantage. And another important thing is that if we can include small scales, then the advantage goes through the roof. So this is obviously very hard to simulate, but it's very promising potential. We're not brave enough to do that at the moment, but yeah.
Question. So this is for weak lensing only, I understand?
Yes, weak lensing only.
And as you say, this will depend very critically on how well you are modeling variant feedback.
Right, exactly.
When you can go to smaller and smaller scales with this,
that's right.
Relying on the information that's gathered.
Exactly, yes. I'll come back to baryons in a minute, because indeed, once you start going to nonlinear regime, you need baryons, and so the question is how good the modeling has to be and how many parameters one needs in the model. So, yeah. Right, so with that in mind, we started working on actually making practical measurements, and that was done with Kids 450 data, which was just public, thanks to the Kids team for making it public. And in the first blinded analysis, we compared apples to apples and neural networks and power spectra. We couldn't directly compare to exactly the same configuration that the main Kids team did, because we needed to cut the data a little bit into patches, which we couldn't directly reproduce their analysis, but I think 10% of the data is a little bit different, but nevertheless, that shouldn't make too much difference in this scenario. And what we see is that, as we expected, the advantage of CNN over our own power spectrum analysis is great. That's what we thought would happen. We managed to shrink the contours in the S8, as well as break this degeneracy that is known to be there between these two parameters a little bit more. Compared to the rest of the literature, our measurements were a little bit higher than the main Kids. but yeah, due to all sorts of different modeling choices and also the fact that we found a value of different values for intrinsic galaxy alignment, and then the main analysis, we think it's a consistent measurement between those two, although with a slightly higher S8 value.
Sorry, Thomas, one
question. Yes.
What is the difference between the left and right?
Right. So the left one is just purely our work. So the convolutional neural net from our own implementation, power spectra, our own implementation on the same exact data. So I said that we needed to cut the images, cut the data to fit into this square patches, and that diverged a little bit from what the kids' original data analysis has done. But we run our power spectrum analysis exactly on the same data. So first we smooth the data, smooth the lensing maps, and then we compute the power spectra. So it's really apples to apples between CNN and 2-point.
Yeah.
And the right one is comparison to the literature, what the kids has collaboration has done.
And I have another question.
Mm-hmm.
How do you estimate error bars for CNN? I mean,
that's a very good question. So here the CNN is learning features that then later we interpret in a Bayesian probabilistic way, right? So if you imagine a power spectrum being, I don't know, 20, 100 dimensional feature vector, depending whether you do tomography or not, then you can do Gaussian likelihood, right? So you have a covariance matrix, you have your feature vector, and then you compute your contours with MCMC. What we've done here is almost the same, right? So we have a feature vector that in our case was just basically the number of cosmology parameters that we were interested in constraining. We interpret that feature vector through a Bayesian analysis. So we create a likelihood of the network output given the truth input, so the simulation parameters. So we can model that very well. And critically also here, we used a variable covariance matrix. So the covariance matrix that we created was actually different for different parts of this parameter space that you see here. So we interpolated not only the feature vector, but also the covariance matrix that was produced in our modeling, likelihood modeling step. Hope that answers your question. Okay.
yeah, thank you. Yeah.
All right, great. Yeah, that's a very good question. Yeah, but so basically the downstream analysis after the network has finished predicting features is more or less the same as everything else we do. Okay, so the next step, obviously this analysis was simplified. We only had 3 parameters. We had sigma 8, omega m, and intrinsic alignment. We did marginalize over redshift errors and shear calibration, but yeah, it was still a demonstration, proof of concept, although the measurement, yeah, it's blinded, so I think it's a very good measurement for Kids 450. We wanted to see if we can bring the machine learning analysis or simulation-based inference with machine learning to a mature level. So whether we can have the same number of parameters spanning the full WCDM cosmological model, and still do this analysis, and whether it's feasible to crunch through a lot of this simulation that spans so much, such a big parameter space. So in the Kids 1000 project, which was a successor of Kids 450, we created a new set of simulations. I'll come back to that. Simulations are called Cosmogrid. And we wanted to see whether we can run it and get constraints. And we didn't want to, this time, for various reasons, didn't want to get much like super precise contours. We just wanted to see if it's feasible. Also, Yanis was graduating, so he couldn't spend a couple of extra months pushing this analysis as far as it could go. So we decided to do it in a slightly lower resolution than last time, and just to see whether we get consistent measurements between power spectra, neural nets, and the kids' official data release. So this time we included baryonic feedback. I'll come back to that. And yeah, we had this new set of simulations. So what you see in this this plot here is how we put the KIPS 1000 footprints on the simulation sphere. So we just basically made cutouts and fit them all together into a full-scale simulation. And here is the blinded analysis that we've done between the convolutional neural nets and the power spectra, and our own power spectra, and the main KIPS 1000 WCDM analysis. So what we can see is that the measurements are very consistent. It's the same data, so they should be. The neural nets and power spectra agree quite well. We do remove some of this. So the KIPS 1000 team is removing some of this area here of the combination of sigma 8 and omega m. This is expected given that we used slightly different priors that they did. So they sampled in a different parameter combination than we did. So that is very well understood here. Overall, the agreement is really good, and this gives us confidence that this simulation-based inference can basically reach this reliable results, even in a blinded way, as the official data analysis from KIDS. It's very encouraging, and currently we are working towards building improved analysis with KIDS 1000 that to go to slightly higher resolution and improve upon this benchmark result, as well as several other projects in dark energy survey, which have the same objective, basically use neural nets to constrain cosmology from lensing.
Sorry.
Mm-hmm.
So because one of your results is that you get improved results, as you said, compared to power spectra. So it is, comparing the blue.
Yeah. So if we compare, so generally speaking, the improvement is there. It's a little bit more visible in the W versus omega m plot, which I think not so much on this one. Yeah.
Okay, right.
But the improvement was was there around 10-15% level, which is also what we expect from a forecast for these moving scales. Like the bottleneck on this was that we still needed to process a lot of the simulation data. I will show you in a minute how the simulation looked like. And we did it on lower resolution just because otherwise we have so many pixels to process. And still the graphics cards that we have available in Switzerland at P-Stained cluster were a bit slow in processing the higher resolution data. So Yanis made a calculation. Can I publish a paper before I finish my PhD? And decided to go for n side of 512 Hilpix maps. Okay, and then indeed, so we processed the data through neural nets, but these neural nets were done on the sphere, right? So we actually wrote a dedicated algorithm for making machine learning happen on the Hilpix grid. So if you're interested in that, there's public code called DeepSphere. It was a collaboration with the Swiss Data Science Center, where we represent the Hilpix map as a graph. And we use the hierarchical structure of Hilpix to basically do this convolutional neural net operations like pooling and creating designed filters. This is a picture from this paper about DeepSphere. Another nice property of this is to a very good degree, this neural net is much faster than a standard spherical convolution. It's not exactly the same as a spherical harmonic decomposition. It has a little bit of an error because it's the graph that we create to represent it is an approximation to the full high resolution pixelization. So it's not 100% the same as ALM decomposition, but it's very close. So, and it's much faster. So it's one of the fastest convolutions on the sphere what you can do with this graph architecture. People have been using it in other applications like weather, geosciences, and so on. And it's being actively developed also by the community. And so feel free to check it out. All right, so this is where we are with constraining cosmology parameters with neural nets and simulations. Just as a side note, we also have a little bit of a competition going on between the machine learners and humans. So human intuition statistics such as peak counts or Minkowski functionals, voids. One can think of all sorts of different features to pre-compute from these maps. And yeah, we have now at ETH Zurich, people working on peak counts, people working on machine learning, and seeing which ones will be better. So this is an example analysis that I led together with Dominic Zurcher, who was a PhD student at Zurich, in peak counts from the Arcunary survey. So you can see the label very well.
You can move the bar.
I can move the bar.
Sure, but, yes. How to minimize it, or just to move it.
Somehow, sometimes it disappears, sometimes it doesn't. So it's
Yeah,
confusing.
you click on the right of it.
You go to more.
Yeah, and
More. Okay.
Maybe you can hide. I don't know.
There we go. Very good. I hope I don't need them anymore. So, right. So this paper was dedicated to shear peak statistics, which means that if we have these simulated and survey measured maps, what we can do is we can look at how many peaks there are. So we identify pixels in the map that are higher than its neighbors. So if you see this little cutout here, will look like this. You can see that there is a peak, and this we would measure how high the peak is, create effectively a histogram of how many peaks there are at what level of height. And we can use that feature to compare the simulations and the data. We did it on the full DES-CR3 data set, and we constrained these 3 parameters that we are actually sensitive to. The other ones we effectively marginalized with a prior coming from other observations. So the peak count functions look like this. So this is the number of peaks if you subtract the number of peaks that you would measure on a noise-only map. So you don't consider any cosmological signal, you measure the number of peaks. Of course, you will have some random contribution there, and you subtract that signal. So you can see clearly that for different values of S8, you get different peak counts, and the question is where the data suggests we are. And so we can use likelihood analysis again to constrain cosmology here. Another interesting thing is that we can do a combination of power spectra and peaks, as well as those two separately. Again, here power spectra were computed from the simulations as well. And we did a tomographic peaks measurement at basically quite conservative scales, not to have to worry about baryons. We did improve by 40% for the combined analysis of peaks and CLs compared to CLs only, but it was not directly comparable to the main DES analysis, given that the choices of scale cuts were a bit different. So, but nevertheless, the results are quite consistent with that measurement. So if we look at what happens between CLs and peaks, we see that especially there's, first of all, they're quite consistent, but there is an interesting difference for the intrinsic alignment and S8 parameter combination. So intrinsic alignment knows properties of how galaxies actually, what their shapes are connected to the shape of the dark matter halo they are close to. So it's a local effect that has a very similar, it looks very similar to what gravitational lensing can do. That's why it's degenerate, and it's hard to distinguish those two things from lensing alone. But if we combine peak counts, one set of summary statistics with the power spectra, different type of summary statistics in a tomographic analysis, we see slight differences in these. So these features respond differently to the intrinsic alignment in sigma 8. And when you combine it, you actually gain constraining power. So this is an interesting hint that the combination of different summary statistics can lead to improved cosmology constraints by breaking some degeneracies in parameterization of our model.
Sorry, Thomas.
Yeah.
One question. So when you do this combined analysis, do you take into account the covariance between the two observables?
That's right. Yeah. Yeah, it's actually quite interesting how to even technically do it, but we do it by compressing the data vectors. Yeah.
Okay.
Okay, so we found quite low value intrinsic alignment, and yeah, a little bit higher value of S8 than the main survey, but it's still quite consistent with everything that DES has seen. Okay, so these are peak counts. And now let me go to the Cosmos Grid simulation set, which was the simulation grid that we run for the KITS 1000 project. It was a large production proposal at the Swiss Supercomputing Center. It took us a year to generate this data. We ran around 500,000 GPU node hours to get this. And we especially aimed at having a lot of independent simulations so that we have a very good errors, or we cover the uncertainty on the map level itself. So we don't only want to know what's the variance of the power spectrum, but we actually, if you have we want to sample the space of maps, right? This is the maps are much longer of a data vector than any summary statistics. So I think there's even a video here. So we run this large simulation set, and we didn't want to go to too much resolution, to high resolution in the configuration of n-body. So the particle size was kind of medium compared to what's possible at the moment. Yeah, we wanted to focus on the intermediate large scales to mitigate the impact of baryons, although we do have simple baryon feedback models in the simulation. So this is the way we structured it. We stored maps at different redshifts. So here you can see these shells counting down from high redshift to low redshift, and you can see how this, for different cosmological models, how this structure evolves when we go in time. Yeah, so Cosmogrid is consists of 2,500 unique simulations nodes. So the grid has 2,500 points, and it's structured in two ways. One is the wide grid and one is the narrow grid. The narrow one is concentrated around the observations, the value of parameters in the WCDM model that we think we know from other observations are the right choice. On the other hand, the large grid enables us to compare the measurements that we make with Cosmogrid to the choices that the main survey usually does, which is relatively wide priors in this. So then also we have another set of simulations at the star. So that's the Fiducial cosmology. There we have 200 independent initial conditions. And we also have derivatives. So we did a little step in each parameter, forward and backward, and run another simulation. So you can get actually the delta map, delta your cosmology parameter, if you're interested in that. On the wide grid, we have 7 initial conditions, 7 runs for each of the 2,500 points. So the total number of simulations in this project is around 20,000 independent n-bodies. With that particular box configuration. And yeah, we store 69 shells. So for stage 3 survey, you can go up to redshift of 3.5, and still you'll get your n of z's, your redshift distribution of galaxies will definitely fit into that. We also store halo catalogs, although quite large halos, and we have the baryonification model, and I will come back to that in a sec. Also, we have benchmark simulations, which have, for example, bigger boxes, more particles, more shells, so you can test whether the choices you make in your summary statistics are changed if you, let's say, have a bigger box, or yeah, whether you're sensitive to the choices that were made in producing of this simulation. So this data is public. So this is hosted at cosmogrid.ai. You can check it out, download it if you want. And use it for anything you like. Okay, so the baryonification is one of the key elements here, and it's a simple model consisting based on the halo formulation. So what we do, we find halos and then use the positions and profiles of these halos to effectively modify the maps a little bit. So what we want to do to mimic the baryon effects is to say, hey, given this dark matter distribution, how would it look if we had a baryon model in it? So it's a kind of a remapping between dark matter and baryonified this matter distribution. So here's an example of how it looks like. So this is the original, this is the baryonified version. And if you have baryonified minus dark matter only, you will have this difference. So first of all, you can see that the color bar is here spans much smaller range than the full convergence dynamic range. So it's a small effect, but nevertheless, it can be important for all sorts of different algorithms. And what it does is basically moves some particles in these shells from the centers of the halos a little bit outside. And it goes through halo model formalism. So we go through this halos, and this is then baryonified on the map level. So it's a bit of a different formulation than the original baryonification, which was working on 3D snapshots. But nevertheless, it recovers the same properties of the maps. So we tested it quite well against the original 3D version. Yeah, and this is currently, there's a fiducial baryonification in Cosmogrid, but you can redo it if you like using this Halo catalog, and even do it on a higher resolution if you like. So
I have
yeah,
a question, Tomasz.
question. Yeah.
So when you do this variant thing, at the training phase, are you trying to fit for the variant parameter, or are you just marginalizing over it?
Yeah, so the question was whether we marginalize or fit the variant parameters during the network training. So for kids 1000, we marginalized them out, right? So we had some fiducial value that Aurel told us this is the way to go. And we marginalized it out with some priors. So we had 2 parameters for baryons. And yeah, one can potentially make this model even larger and reprocess this data to get it.
Do you think learning the baryonic physics would help you in any way? Does it break any degeneracy or something?
Yeah, the question is whether learning baryon physics could help and break degeneracies. Yeah, I think if one does a higher resolution analysis and is able to reprocess Cosmogrid with more baryon parameters, just technically totally feasible. It's just time and computing time also. Then yes, I think one could try to do it. Yeah. Okay, so I'm getting running a little bit out of time. So maybe I'll go to yeah. So I mentioned that already. So we have this fiducial model plus and minus derivatives for all the parameters that we have in our grid. One can do it also for baryons. So you can see for the same map how it would look like for if we change the value of some cosmological parameter a little bit. So this is basically a derivative of convergence with respect to cosmology parameters. So there are training schemes that can employ that, especially information maximizing neural nets, which Yanis actually used in his project, but it's not necessary. Okay, another feature of Cosmogrid is that we have this shell permutation scheme, which is relatively novel. So Cosmogrid was run in a box replicated scheme. So we have a box, and we basically replicate it multiple times all the way to as far as we need. And in our case, it was redshift 3.5. And at each time during the evolution, the shells are stored, right? So technically, if you look at the specific lines of sight, you could hit the same point in a box at different redshifts. So let's say for that I could use a pointer. So let's say you go along this line, right? And these are the box. This is the box size. This goes all the way to high redshift. So if you go along this line, you could hit the same point at multiple positions. So this goes to 3.5. So if our survey has a redshift up to, let's say, 1.5, we are only I think we are only hitting roughly 3 boxes. So it's not that terrible. But what we can do, given that we have 7 simulations per grid point, we can take this part of the light cone from one simulation, then this other yellow one from a different simulation. So you actually never hit the same point. So of course, if you cross from one box to another, you look at it at a different angle, and that for photometric survey, which broad redshift bins, is totally fine to do. There's been a number of papers showing that one can rotate your simulation box and project it, and that works well for the for the 2D probes or two tomographic 2D probes. For 3D, it probably would be different, but that's a different story. And yeah, so that given that we have a number of 7 simulations per point, we can use that box replication scheme, shell permutation scheme to get this avoid these effects and further bring the simulation closer to the true cosmic variance that we would have if we had infinite computing resources. So yeah, this is a nice feature, and one can also test it with the big box benchmark, which looks like this. And so the boxes are twice as big. You can see whether you can, to a good degree, test all these assumptions with these big boxes. And how it is comparing to the other simulations out there that can be used for map level inference. So Cosmogrid has, well, the previously most commonly used simulation is called CosmosLix, that was developed for the kids survey. And Cosmogrid is basically much larger in terms of number of parameters, number of simulations. But the difference is that CosmosLix have much better resolution. So if you want to go to small scales, CosmosLix offer better, well, could go to much smaller pixels, although they don't have Baryon feedback models. So it's a bit of a difficult set to use in practice for at this moment. I think they're working on it though. So yeah, this is the first simulation set I used for peak statistics paper in dark energy survey science verification. So it was the first time we were doing this, and we progressed a lot since then. So this is that. Okay, I encourage you to look at the data. You can download all of it at this website, and it's very fast to transfer via this Globus. So this is that. I have some other material about breaking degeneracy, so maybe I can try to do it in the last couple of minutes, and I will probably skip this part for the lack of time, but yeah, is that okay? Yeah. So in this prototype analysis we call DeepLSS, we combine probes of lensing and clustering in a similar way that a survey analysis would in the standard 3x2 analysis, which is currently the objective key project in all of these big surveys. So in this analysis, I wanted to see, is there a further benefit of combining probes? Can AI learn anything more if we give it more data? So this is an example of weak lensing maps with 4 redshift bins and corresponding clustering maps with simple linear biasing prescription. One can also make intrinsic alignment maps relatively easily with NLA model and plug all of that into a machine learning method. So in this paper, which was published in PRX, we had this relatively open model that has cosmology, intrinsic alignment, biasing, stochasticity, and evolution of bias and intrinsic alignment. And we managed to actually improve by quite a lot the constraints, especially on intrinsic alignment. So you see this really breaks this degeneracy remarkably well. And I spent almost 3 months trying to understand why, because I was very surprised. But yeah, it seems to be working very well, and I'll give you an explanation in a sec. So this was, again, apples to apples power spectrum and deep learning run on this very open model on this data that you've seen. And yeah, it's basically a forecast for roughly 900 square degrees, KITS 1000 level of data. This is the zoom in on this, just to see how big this gain is. And main idea that can explain how this works is that neural nets can connect specific areas on the maps. So if we have the convergence map, so the lensing map and the galaxy density map, is really connected very well and basically pull the information from specific regions that are and ignoring the rest of the map, right? So a standard cross correlation would just correlate all pixels with all other pixels and not pay any more attention into any specific areas where we think the information is coming from. but neural network can learn this. There is a literature actually that I found later about marked correlation functions, which can achieve something similar. So you basically weigh your correlation function estimator by some function. This is in Redshift surveys, people have been looking at it recently to further boost information gain. So the neural nets do it pretty much automatically. So how do we find whether this is the mechanism? We can look at something what is called the sensitivity map. So if we have a response of our summary statistic that corresponds to a given cosmology parameter, in this case, it was the intrinsic alignment amplitude, with respect to the pixel on the map. So if we make that pixel smaller, our intrinsic alignment will go up. So what the network is doing is looking at, first of all, it looks at this galaxy over density map, finds some region here, and then it goes to the lensing map and says, okay, in this region, I need to use these pixels to give me the information about what the shapes of galaxies are, how strong the signal is, and it ignores all the rest. So here, if there's a color that is away from white, that means the pixel is important, and it can be either blue or red. Blue means a negative derivative, red means positive. And so this is the sensitivity. It's quite standard in machine learning actually to look at these. They're also sometimes called saliency maps. So yeah, it's basically pulling the information from this region in this map and ignoring the rest. And this is pretty much it. So you don't dilute the signal by averaging all the other pixels. Question?
So this sounds very good actually, but so I was wondering if there is a systematic that actually is in the map that for some reason enhances, delta G in that particular spot. So
right,
maybe you will be biased by this particular feature, right?
Yes.
So
yeah.
In a way, you are at the same time being more prone to be affected by specific systematics in certain regions of the map.
Mm-hmm.
That when you use the full information, maybe you are more robust, right? So there's some risk in the
Yes,
as well,
absolutely.
Yeah. Okay.
Yeah. So the question was whether this includes improved sensitivities, also increases sensitivity to systematics, and absolutely yes. So we have to be very careful here with if we want to use it in practice, we really have to step our systematics game by quite a lot. I mean, this is of course expected. The more benefit we have, the more careful we need to be. So yeah. And this is basically just illustrating that.
Yes.
Yeah. Okay, so I think I'll stop here, given the time, and I won't talk about this, but if you can ask me later about this part if you're interested. Okay, thank you.
Thank you. Thanks a lot, Thomas. Any questions in the audience?
So about your last slide, is it possible to, in general, to learn how the machine learning is doing the analysis to deduce a strategy for human intuition?
Right. Yeah, the question was whether one can use machine learning to learn how to what it's doing and how to use that knowledge. Yes, so there is a field in machine learning and AI called interpretability. There's even a really good book on interpretability recently. It's mostly developed for natural images. Those are much more complicated than the data we have here. So also the interpretability strategies are much more complicated than this simple sensitivity analysis that I've done. So yeah, you can check it out. And there was a paper actually in Nature Astronomy about learning from deep learning in context of lensing. So what they've done there was look at the filters that the network was producing, and then just disconnected the filters from the network, use these filters to create features, and then run a likelihood analysis on the features. And then we found that actually, yes, it's very beneficial to use these filters. When you look at these filters, they kind of look like peaks, actually, which was reassuring. But there were others that were kind of surprising. So yeah, I think there is potentially quite a lot of exploration one could do in this area.
So, well, I have a question. So here you are combining, when you say they combine the DeepLSS, basically galaxy clustering and lensing. So this is the 3 times 2 point basically standard analysis, or what is that exactly?
Yeah, so it's a bit different from 3 times 2 point, but it follows kind of the same idea, right? You want to combine, yeah. So here the difference is that we actually didn't have there was a forecast, so could do whatever we want. We had 4 tomographic bins, and we didn't have the lensing bins and the lens bins, so we didn't have like clustering or maglim or red mapper, red magic galaxies. We just used the same bins, but yeah, one could optimize even further by doing optimization of binning strategies. I mean, that's typically done for 3 times 2 point, right? So yeah, there's a difference, and yeah, it connects the data on the map level, right? So you get the correlations much earlier on like pixel to pixel rather than feature to feature at the end.
Yeah, I mean, the gain, when you say, okay, the gain with respect to traditional analysis would be with respect to a 3 times 2 point.
Yes, that would be the way to compare it, yes. Yeah.
So I have one more,
Martin, yeah, go ahead.
but this is an not very well defined question. So what would it take to make this kind of analysis a standard
Yeah.
in the field?
Yeah, sorry. The question was what would it take to make this a standard analysis? Yeah, so we need a lot of computational resources, a lot of simulations. We need a very good understanding of systematics and modeling also, of course, yeah. Depending on what scales you're interested in, but even for moderate scales, I think modeling of, yeah, galaxy biasing, connection between dark matter and galaxies and selection functions, everything becomes a bit more difficult. So I think it's a nice advantage, a lot of responsibility, but in the future we'll have better computers, we'll understand the systematics better. So I think going forward, it's not a 3-year project, but maybe 5-10-year thing before it becomes like really competitive. Yeah.
But there is nothing rooted there is no intrinsic limitation.
Yeah, if there's a question of whether there's an intrinsic limitation, I mean, I don't see one now. It's just doing everything on a simulation level rather than on 2-point level is just much more challenging when it comes to both modeling and data processing. So yeah, I think that requires time and computing resources. If we assume we have that, then I think it's okay. Yeah.
So I had some additional question. So how important is to have, I mean, a very good set of maps to train these networks? I mean, do you need, is a critical number of these simulations of you sample the parameter space, so below which everything fails, let's say?
Yeah, it's a very good question. I don't have a good intuition for that. That's one of the reasons we just decided to go for a lot of simulations in Cosmogrid. I know that in KITS, if we look at the Cosmos simulations, they don't have a lot of nodes, so the grid points. So yeah, here, although I think they have more now since they published the paper. They were trying to do a machine learning analysis, but it didn't quite work very well. So my intuition is that you have to sample the parameter space quite well, but you don't need to necessarily have a lot of points, a lot of independent simulations per point, right? So you can go for covering the grid more densely rather than covering a point more densely. So there are some choices to be done, and maybe that's also an interesting way question to study.
So the sample variance is not so important; it's more sampling well the cosmological parameter.
Yeah, for cosmic variance, it's the total number of simulations. It doesn't really matter where they are on the grid that matter, because the machine learning can kind of not only interpolate the signal across the grid, but also the errors of the signal. So it can connect these points in terms of variance as well.
Any more questions? If not, let's thank the speaker again.
Thank you. Okay. Thanks, Martin.
Thank you very much. Thank you.
See you.
Very nice. All right.
Thanks. Okay, so I can start.